It's flows, it's like linear
Just got his Ashwin submitted his email me all day, and it, oh man, I kept emailing. I already had 3, so it wasn't a big deal, but it made my application stronger. Yeah. And at like 4:30, he emailed me. He was like, "Oh, just go back to Durham." I'm like, "All right, right." So I was calm. I was like on a flight.
When did it actually say like submitted or whatever? It was
right after.
Like right after.
Yeah, it was pretty much right after you left.
No, there's
so many that I barely got my undergraduate professor to submit yesterday. Didn't have Pankaj just submitted today after getting back from a 3-week vacation. And Ashwin submitted half of it.
And there's
It's my fault. I emailed everyone on Monday.
yeah. I was like I submitted like an hour before too. Quite a crowd. The U2 one was pretty crowded. We had a bigger room for the first one, so I don't think more people around. But we were like
Should get started.
Yeah.
All right. So, what questions do you guys have?
You did approximation.
Can you explain the knapsack for approximation?
Sorry.
Can you explain the knapsack approximation?
Right.
Which the PTOS.
In terms of approximations, did you say we didn't have to know like too many specifics, just like mostly conceptual stuff?
And for the last one, or there's some like notes that are still, that's the LP rounding.
Oh.
So we saw an LP rounding algorithm for vertex cover, which is like fairly straightforward. Which is all the LP rounding algorithms for that is to solve the LP, the fractional LP, and then just do like a threshold thing. That if look at a variable, if it's at 1/2 or above, round up. If it's below 1/2, round down, and that gives you 2 approximations. So, but we're not gonna have you like. It'll be like some conceptual question if you have any LP rounding questions. But the first one was on. He explained the PTOS for knapsack. So first is like the idea, like the concept of a PTOS makes sense, or not so much. So the idea is that you have your approximation factor that you're going to get is you'll get algo on any given instance. So this is okay. Before we go to what a PTOS is the idea of an approximation algorithm makes sense in terms of what you're trying to do there. Is that you have some NP hard problem that you don't know. We don't know the exact algorithm that solves the problem in polynomial time. So what we're doing is we're settling for an algorithm that runs in polynomial time, but then doesn't always output the optimal solution. But we are able to, based on how we define the algorithm, you can provably guarantee that whatever solution it outputs is within a multiplicative factor of the optimal solution. So like here, this is for a max problem. So here, forget about the 1 minus epsilon. We just say something's alpha approximate if no matter what the input instance I is to the problem, that the cost, this is the cost of the algorithm, is greater than alpha times the optimal. So here for a max problem, alpha will be between 0 and 1. And the better you have an alpha, the alpha equal 1 approximation algorithm, then it's just exact. That every time you're outputting the right answer. So does that idea make sense in terms of you're giving yourself the ability to run an algorithm that runs more quickly, but because you can't solve it exactly in polynomial time, or we don't know we're going to solve it exactly in polynomial time, you're allowing it to relax how good of a solution has to be. But it's still a guarantee that we're saying it's never too far away from the optimal solution, and that's what you try to prove. And for a min problem, you flip this. You say alpha would be at 1 or above. You'd say algo, the cost of the algorithm is less than or equal to alpha times alpha. So that's where like a 2 approximation for vertex cover. There you'd say no matter what vertex cover you output, that the number of vertices in that vertex cover is never twice the number of vertices in the optimal vertex cover on a specific instance. Is that good for give you an idea? Oh yeah, so for PTOS, so there's some problems where you can get arbitrarily close to an exact answer, but then your running time, so the idea is that you parameterize the algorithm by this parameter epsilon. And so at a certain, you give this algorithm this parameter epsilon, and at that point that's a fixed constant with respect to the algorithm. And then we're going to say the algorithm is going to run in polynomial time, but that polynomial is going to show up, is going to be, the running time is going to be inversely proportional to this constant. So we say like runtime is equal to something like, I don't know, what does it end up being, like 1 over epsilon to...
Or 1 over polynomial.
Yeah, 1 over polynomial. Right. So 1 over, so like poly of 1 over epsilon, I guess you say. It's some function of like n or something like that. So the bigger, the smaller we make epsilon, the closer we get to making one approximation, the bigger this like blows up, is the idea. But since once I give it epsilon, we now think of it as a constant, this still like runs in polynomial time. So I guess the best way to say it runs in poly of both 1 over epsilon and n or something. If n is the size of the number of things you with. So I forget, does anyone have the running time of, what does knapsack run in?
It's n squared p, so it was like n cubed over epsilon.
It's just n cubed over epsilon.
I think so.
And there's this distinction between like fully polynomial time approximation scheme. So that's what PTOS stands for. This is called approximation, polynomial time approximation scheme. And there's kind of a distinction between just there's an FPTOS and a PTOS, but I don't know if you went over that, but don't worry about that. Just like for just the idea of this like passing a parameter in at this epsilon in, and then that idea is that the closer you make epsilon, you can never set epsilon equal to 0, because then you have this 1 over epsilon showing up, and you have an unbounded running time in some sense. But you can make it arbitrarily close, and then once it's a fixed constant, then you get a running time that looks like this. So we're not. I don't think it's going to be very beneficial to like walk through. The idea with like knapsack is that. So what's the problem with the pseudo polynomial time algorithm So how does that work? The pseudo polynomial time algorithm for knapsack. So the exact, it's a dynamic programming and it's an exact algorithm. What's that?
It's n squared p's. Oh, n
Yeah, so that runs in like, so the exact dynamic program, that runs in like, if the, like you can do it in a couple different ways, but like one is like, if k is the capacity of your knapsack and you have n items, then it runs in like k n time. And so you have a table entry for each possible like max capacity you could have, and then for each like item 1 up to n, you have a entry for each of those, and then you solve. You can go back and you go through and look at what the recurrence is for that. But the reason why you don't need all this precision necessarily to come if you're able to relax how close you come into the solution. Like if you have if the weights of your and values that you're given are very large and they all have they each have like a significant like digit. It's like 1 million, 100, 500. You know, there's not a lot of like if you have like weights that have let's say all these like very specific like they have non-zero digits like in the hundreds place or whatever, and the tens and ones. Is that really because like the bulk of the solution, let's say these are our values actually, the bulk of our solution is going to come from the fact these guys are in the millions. So the idea with that is that we like rounded our values by basically saying that we're going to look kind of, instead of treating this as something that's like 2 million or 1 million, we just maybe like depending on how much we're willing to lose, maybe we just treat these as like 2 and like 1 instead. So we basically we treat all of these like they're zeros. And how we rounded it, I mean how close you come to getting an approximation, but how close this approximation is like how many digits you're willing to like chop up. So like the more digits you're willing to represent or in your solution, the bigger that's going to come closer to doing something like this, where you're doing the polynomial just like the dynamic program itself. But if you're willing to lose like a factor of a half or something, then you don't need all this extra information because the bulk of the solution just comes from the most significant digits. So that's like at a high level like what you're doing. You're just like cutting off the precision in some sense and running it on a less precise instance. And the amount of precision you get is like just based on how you pick epsilon. Is the idea. So maybe if it might be a good idea to go back, kind of, I don't know if you had that like high level and like intuition when you like went, but going with that in mind, it might be a good idea to try to like go through that proof and see like where that's showing up. Is like where is that rounding or cutting off the least significant digits showing up. Okay, so I think does that help for
Probably I didn't understand it all. It's like the scaling part.
the scaling part? I mean, this is like a high level what you're trying to do with the scaling. You're just scaling it to some less precise instance, and you're willing to lose like the optimal solution. You might be off here because you're just ignoring the fact there's all these extra digits, like up to like a factor, like whatever you chop off.
It's more important, like Nat said, to understand how approximation algorithms work in general. So, right? If we're doing exact algorithms, you have to prove the running time and the correctness. For approximation algorithms, you need to prove the running time and correctness, but it doesn't need to output the correct answer. It has to output an answer that's within like the approximation factor, whatever that is. So if you understand that, that's the key thing with approximation.
Some more questions or anything from like the first half that you totally don't remember, or like are people feeling good about this exam? Or?
What are the topics that are on the final?
Just the topics.
It's
I
everything.
mean, it's everything pretty much. I mean, we can kind of go through and kind of
Yeah.
regurgitate the
Questions.
I don't know, like the
Skimming the
Syllabus,
topics
but-
from the lectures page on the course website it'll be the best thing. And just looking through the lecture notes headings and stuff to figure out all the topics. But that's how we wrote the exam. We just went through the whole lecture notes page and looked at all those topics and picked things out of there. So.
Are we going to have enough time to answer all the questions?
Yeah.
Also, it's like more like the midterm 2 rather than midterm 1.
Yeah.
Yeah, I mean, it's hard to guess how long people are going to take on certain questions. I think it'll be somewhere in between. I think that's what Demalia was like telling people. He told that us like when we sat down and wrote it. He said he wants the difficulty like harder than the second midterm, but not as hard as the first midterm. Is the idea. You have more time, so it's 3 hours.
It's twice the length of midterm 2, but you have more than twice the time.
But then it's hard to get like how long are certain questions going to take.
Yeah, go ahead.
Can we go over like a question from the book on the dynamic programming that you guys put up?
On the dynamic, yeah.
Yeah.
Okay.
Yeah, what's the question?
Maybe it was 522.
522 and
In the
and the big one.
Yeah.
Do you remember what like?
I can pull it up.
So I think what is that? That had like that palindrome one.
Yeah. I think the palindrome one is the one that I was.
So that's like 5.2. So that's the.
Just find like given any sequence of characters, find an O squared algorithm to find all the longest palindrome.
So it's a DPV. It's an O n squared time. Okay.
So now Nat and I have to try to figure this out.
Yeah. So when I posted all the solutions, I saw like, well, that looks about like I think I could solve that and like the amount of time for the exam. I didn't like.
So we can do that in the final too, right?
No.
The question.
You guys are supposed to be. This is your.
The solution is trivial and left to your degree there.
Yeah, you do what you have to do. So you're just given some. Okay, so the problem is you're given. Try to keep things on the same. So you have like n squared. What? You have, so you have n squared time, so you should be good, right? So you're given some like string. Okay, so the problem is asking. So you're given some like n character string, and it just you're trying to find the longest substring in S that's a palindrome. So like here, so there's like multiple like contiguous substrings. So it's not like it's a subsequence thing where you can just pick out like whatever character you want in between. It has to be like some contiguous like substring in the thing. So here, like, here's one palindrome. Any single character is a palindrome, but like I think like the race car is going to be the longest one. Okay, this one isn't very hard to solve, but so I'm thinking that. So okay, how about does anyone think they know how to solve it in the audience first before I?
I think I know how to solve
You know that's all. Sam knows how to solve it.
You can loop through and expand. Right?
What's that?
You can loop through and treat it as a center and expand outwards.
Loop through and
So you
expand.
treat Z as the center. Then after that you try to check left and right. So no, then you go to H.
So you're thinking like a left-right thing?
Yeah, so you expand, like if you treat H as a center, then you expand outwards.
But how do you know what to treat as the center?
Like you loop through everything and the current character will be your center character,
Mm-hmm.
and then the longest you can expand to is the length of the thing. And you loop through everything as.
So I'm not sure how I see that's if that's dynamic programming.
But it's not default.
Yeah, but it's, you're allowed n squared time, so it's.
Yeah.
So can you do it faster or something? This seems like trivial. It's like n squared. So you just treat everything. You pick one center. If there exists a palindrome.
But then, what about odd
Yeah, it's all.
lengths of characters? Can't be centered.
Oh, okay, yeah.
You can, so you treat like single. You can go loop through for.
Yeah, no, you just every in between you can treat as well. That only adds
So it's constant.
another n thing switcher. What's that?
So it's n times n.
Yeah. So each one takes. So that's n squared truly. So but it's what it says n squared dynamic programming. Or does it say faster?
Yeah.
I'm thinking you can do this in linear time. Okay, well if it had to be like that's just kind of just like a brute force way of just like checking all the solutions. I think like a dynamic programming solution would be like the longest. So if you do like Optivi is the longest. Okay, this will just go over the structure of like what a dynamic program looks like. So longest palindrome in substring.
Longest palindrome ending at some string.
Yeah, I'm just saying substring 1 through I.
Yeah, but that won't work. Has to be ending at I, right?
I'm gonna say ending. Yeah, that's great. So you'll just say
Okay.
so that you're just gonna take the max between I minus 1. And then if it ends, otherwise it has to end at, there is a longer one.
So
So it either doesn't end at that one, or it does end at that
yeah,
one.
okay.
You just go through and check to see if there's a.
It's the same thing.
Okay. Actually, let's try to do. This is a bit of a disaster. Let's try to do a better one. Is there?
Wait, what's wrong with this?
yeah, I pick this problem.
Okay, fine.
Uh,
Meeting. Okay, so if this is our, we're gonna have
Does it
n
have to
different
start at
entries.
one?
What's that?
Does it have to start at 1? Because some of the examples they give are, I mean, like race car.
Right. So how do you? Okay, so we'll just go through and do this. So there's two cases for the length of the longest. Let's say this is the length of longest palindrome in that substring. So either the longest palindrome in the substring ends at the last character, or it doesn't. If it doesn't end at the last character, then what's true? What is this equal to?
so obviously I means the one that before it.
So it's just whatever, you just look at the best answer you had for Optivi minus 1. Since whatever, if it doesn't end at the I string, then it has to end somewhere in between.
Okay, but since it's a palindrome and you have to have a point of reference at the beginning of the thing too, how do you take care of it? Because like you can't add it on to the end unless it's also at the beginning. So
What do
how
you
do
mean?
you have a way of referencing back to the beginning of that word?
Referencing back to the beginning of
You see what I'm saying? Like if you got to like race car and you just left off the R at the end,
Mm-hmm.
like you have to have a way to know that that R is at the beginning because it wasn't a palindrome before, but you just added that last R. So now-
Right, yeah. So that doesn't, but this isn't,
So I think it doesn't.
this can't be, if there is a palindrome that's longer than race car before we get to here, then that'll take care of this case. So if we're at R, as you're saying, where the
Yeah,
I
you're
equals
about to
whatever,
add R, yeah.
yeah, okay. So that's what we need to compute for this case. Right. So.
I guess what you're saying is like if you add R, you also need to add R backwards in the other direction, right? Whereas your previous longest palindrome was 2 shorter than your current palindrome. Right?
Right. So we need to, I mean, if you're at R, if you're at the case where R is going to now contribute to a palindrome, that's going to be We're saying like the two cases we're deciding on is either the last character is included in the longest palindrome or it's not. So this is the case where it's not. So now we need to still fill in the other case as well. Yeah.
Yeah, I think for this one, should it be like OPT I like comma G? So we start from the S1, then like can be from I to I plus 1, then I to I plus 2, then up to the very end of the list.
I plus 2.
So
So you
it's
want to
like-
do a two-dimensional
So
one?
it's like we look through the whole thing n times, and then for each loop we take like O(n) time for the dynamic programming.
But if you have ij, you're saying that you have n
So,
squared
I mean,
entries
like,
to
if
fill in now.
we just assume that we include the S element for that scenario, and then we see like how long the thing can be.
Okay.
And then
So then you have n squared entries to fill out. But then it's taking n time for each entry that's n cubed.
yeah, so it's like, it's like
So as soon as if you have a dynamic program where you have n squared entries to fill out and you need an n squared algorithm, it's probably the case that you're
yeah,
going to
yeah,
have
we can
constant
figure
time. So how do you do that in constant
that.
time?
How you want constant time.
You have to fill out each entry. So the nice thing about this is that we can still take O of n time to fill out this and still hit n squared because I only have O of n entries, n entries to fill in. So that's something like if we say here, solve this in this amount of time. So if you have like something, so if it asks for an n squared algorithm, there's probably two cases. Either you're going to have like a two-dimensional, if like the thing that you're like working with is like n things long, either you're going to have like a two-dimensional one where each entry takes constant time to fill in, or you'll have an single or a one-dimensional entry or table to fill out.
Yeah, I think we can have a two-dimensional with like each entry is constant time to fill out.
Okay, so you think that's constant time?
Yeah,
So
we
maybe
can
we
have
just
two
like finish like that might work. I mean, if you want to talk offline, but as well. But I think this is so like
we are doing one-dimensional now.
so like how does I mean this is basically going to turn into like a brute force like if we're allowed n squared time. So given in the case that we do include the last character, how do we go through and check what if there is some palindrome that includes this last character? How do we go through and find the longest palindrome that ends there?
Go through from the beginning of your substring and find the first instance of that last character, and then move back one and move forward one. If that doesn't work, find the next instance.
So this is going to take n squared time per entry.
Yeah.
It sounds like.
It's simpler than that. Although I do think that
Is it
this
going
needs to
to?
be the longest one ending at I, or else it won't work.
So how's it going to? Yeah, we'll fix it if it's
So
wrong.
why did we go from like J to I or something? Why are we going from
Yeah,
1 to
yeah,
I?
that's what I mean.
What's that?
So like you said longest palindrome substring 1 to I.
I just don't see the substructure there. So if you wanted to do like a J to I thing, where you're looking at you're saying that your table entry should be the longest one from J to I instead.
So do we have a one-dimensional table here, or is it?
Yeah, so that's what I'm setting up, and what he's suggesting is
Okay.
that we change that structure and say
I
IJ. But at that
Yeah.
point, I don't see an easy way to.
So the way to do that one is
You just go
the question is the substring from I to J a palindrome, and you can figure that out by taking two smaller substrings, figuring out if they're palindromes, and then I just need to add on one character. So yeah, that's fine. Then you're filling out an n squared table, and you can do each one in constant time.
Yeah.
So that's one dynamic program that
I
works.
didn't know we were in a one-dimensional table here.
Yeah. So I think this one will work also, but that's a good point. That one works. So does everyone understand that approach? So the question is substring I through J a palindrome? And normally it would take linear time to figure that out. And I need to answer n squared of those things, so I can't take linear time for each one of those. But if I use dynamic programming to figure out if the subsequence I to J is a palindrome, I can use the subsequence like I plus 1 to J minus 1, and then I just check to see if the first thing and the last thing are the same. And if the smaller thing was a palindrome, then I know this new thing is also a palindrome. So I can do it in constant time. Yeah.
That like doesn't include cases where the two substrings aren't either palindromes, but together they're both halves of a palindrome.
No, I'm taking the smaller substring.
One in each end.
one on each end or something.
So in that case, what's you're saying? What's the question? Opt of ij is the longest one, where you're forced to. Sorry.
First and last letter is just the same.
So I can figure out all the single entries, all the single letters. They're palindromes,
All the double.
and all of the pairs, if they're the same,
Yeah.
are palindromes. Right. And then to get the rest, to get I to j in general, I look at I plus 1 to j minus 1, and I think that should work, right? Yeah.
So like in general for these dynamic programming problems, would you recommend trying to set up a table, like if it's n squared, would you recommend trying to like first go to the n squared approach instead of an n squared size table that takes constant time? Or like
You just try to like feel it out, like it.
Yeah, that's all,
whatever.
it's hard to answer in general.
Okay.
Yeah, feel it out. Try different things. But I mean, it's going to, you have to, however much time you're given, like n squared or n cubed, you're going to have to divide that up into how many problems you get to solve and how long you're going to take to solve each of those problems. And if you remember that and you just try a few things, right? Say, well, I can either solve n problems with linear time each, or I can solve n squared problems with constant time, and you play around with the possibilities. Think about what subproblems you have.
Okay, so completing this. So the suggestion is that we need to do it instead the longest palindrome.
So you can also do it this way. This works as
You're
well.
saying ending at I is the
Ending at I.
character.
So this is a linear size table and takes linear time, right? That's what this one will be. This one will be.
Yeah. So the idea is so if you have a linear size, you're allowed to take O of n time for each entry.
Yeah.
So you just need in this case my is.
Yeah. So now to figure out if I should like if opt I is the longest palindrome ending at I, and I know what opt I minus 1 is, say it's like 5 or something, how can I figure out what opt I is? So someone's point, I forget whose point before was right. How do I need a reference point. How do I go back and figure out which character I need to check to make sure my new character is the same? Yeah.
So don't you need to know whether or not you're like in a palindrome at I minus 1?
You're always in a palindrome. It might be a length 1 palindrome, but
So if like, okay, so if the longest palindrome is substring ending at I, that doesn't mean that like there's a longer palindrome that you already passed, right?
there could be a longer one somewhere else in the string. So I'm saying there's a palindrome of length something. I want to figure out the longest palindrome ending at I. So if I know the longest palindrome ending at I minus 1 is like 5, right, I have some string up until now, and then I have a new character. And I know I've got some palindrome here. Which character do I need to check to make sure I'm making my palindrome longer, or do I need to start over a new palindrome? Sorry?
Like 6 back.
6 back, right? So if opt I minus 1 is 5, then I know I need to check 6 back and see if this one is C. And if it is, then I'm still in a palindrome, and then opt I should be 7, right? And otherwise, it should just be, I need to check. I need to check.
So actually, so I was getting caught in the fact that n squared is just like there's brute force. There's only n squared like possible so you can do a brute force algorithm n squared time. This is gonna actually give you linear.
Yeah.
Because they're actually any constant each time. So
Actually, this won't work because you can have this won't work for palindromes inside palindromes. So never mind.
wait, what's this?
Yeah.
So no, I'm confused what it is.
So if there's a C here, I can't just take 1 if there's not a C here because there might be like a C here part of the palindrome and it creates the start of a smaller palindrome or something. Maybe it still works. I'm not sure how to analyze it, but the I to J thing with constant time definitely works. So I think that's the punchline here.
I'm still not convinced you can't do it in linear. Yeah, I don't know.
Can't do it in linear.
Who knows? Here, we'll make it up to
We
you.
can
We'll
figure
send
it
out. Yeah, we'll figure it out and send you guys the solution. Sorry, it's
Is there, generally when you're doing dynamic programs, is it easier to figure out the recursion and then build up? Or is it easier to just start by saying here are the base cases and here's what we can solve from that?
I mean, it's kind of like a bang bang thing. So it's
I would say definitely figure out the recursion and build up.
Okay.
That's my advice.
yeah. So just start looking for like what like you always just start asking like what if I have some smaller solution. Like, how can I extend some smaller solution to a larger solution? And that's what we're trying to do here. So we're just not quite sure about, like, well, what's the right way. That if we have some small, like, what can we say? If we know, like, the longest, like, palindrome, like, if you're, like, starting with, like, a linear structure, just I'm going to say off of I, is, like, the best I can do for 1 up to I, and then to see if you can make that work. That's probably the first thing I would try. If you're given something, regardless, like, the random time. Especially if it's linear, that's probably the first thing. Like, is there some constant time thing that I can, like, extend? But then, if that doesn't work, if it's like, well, I just don't have enough information, and then maybe you're like, well, no, I need to do from like I to J instead. Like if there's like, and then you see if you have like some, like, if the substring from I to J instead, you can extend it anyway. Then, oh yeah, it's hard to say because like it just requires like looking at the problem and like kind of using the structure of the problem to like extend solutions. It's not something you can't come up with like a recipe to like do these. You just kind of have to get practice. But
Yeah.
And for this one, it breaks the simulation. We have to fill the table diagonally out. Is that weird?
You would need to, I don't know about diagonally out. You would need to fill it in by size, right?
Yeah.
So I don't know which way in the table that is, but it's just, I need to fill out all the length 1 things first, which is easy, and then the length 2 things, which is easy.
Exactly. You're going like this up and then depending on which way you do in the matrix. But yeah, the one diagonal is like the ones the diagonal down the middle are the one length one.
Yeah.
And then you move it. Yeah.
And then I'll fill out all the length. I'll fill out all the length 3 ones from the length 1 ones, and then I'll fill out all the length 4 ones from the length 2 ones. Yeah, and then build up like that.
Yeah. Don't describe how to fill out the table. Like just say.
Well, a little.
You don't have to say like diagonally though. Like just say just when
Yeah.
you're analyzing your runtime to say if we can do it by length. You don't have to say like it ends up being this like diagonal thing or whatever.
Yeah,
If we
exactly.
for each length up to this amount, if we know the answer to the smaller length problem, we can answer this in constant time.
Yeah.
And since then you can. Yeah.
The important thing to say is that I can fill out this entry in the table using just these 2 entries in the table, and that's a constant number, and therefore I can build it up in constant time for entry. Yeah.
So it seems like the dynamic programming problems we should be expecting are closer to lecture notes than the ones from DPV.
Which are more with graphs, maybe, or what do you?
No, they tended to be like 2-dimensional.
Yeah, they tend to have like 2 parameterizations, like as in like you'd be moving like 2 things at once in an object. Like it would be like probability, or,
That's possible. You can have 2 things, but
So like what are the
in
was
general
that one from DPV this palindrome?
Yeah.
And then what are some of the other ones we gave?
like probability of exactly k heads and coin flips.
Yeah.
we gave that as a practice problem.
We did that in
sometime.
the first review session, so that's not so.
Yeah. I think that was actually a problem on last semester's algorithms exam.
Yeah, I mean, I wouldn't just say like, oh, it's more likely to do a single dimensional one versus a 2-dimensional. I mean, we did some like 2-dimensional ones, right? Like Bellman Ford is 2-dimensional. We did like a 3, like Floyd Borshaw is 3-dimensional, right? So like, I want to get caught up on like the dimension. I mean, it's hard to think of another 3-dimensional one. So it's usually they're either like 1 or 2. Yeah, sorry. How about that? Any other things people want to look at? Everyone perfect on flows after that wonderful homework you guys. Homework 3.
We go to like randomized like for like the edge contraction stuff.
Okay, so it's probably more like first off, just like knowing the difference between Monte Carlo
Okay.
and Las Vegas. So like, what is that difference?
The Monte Carlo has deterministic runtime, the non-deterministic solution.
So what do you mean by non-deterministic solution?
It's close to right.
Okay, so it may not be right, but what's the requirement on how often is it allowed to be wrong?
The next one. Oh.
Whatever that.
It has to be
Do you want me to do this
with
one?
high probability,
Yeah, that's
right?
I mean, if you want to break. Stole the eraser. Thanks.
All right, so the Monte Carlo algorithms need to be right with high probability. And with high probability means something specific. It means 1 over a polynomial in n. Sorry, it needs to be wrong with something like 1 over a polynomial in n. So like if it's wrong 1 over n squared at the time, that's a Monte Carlo algorithm. Okay. But the running time has some upper bound, and that upper bound is fixed and never goes over that. So that's Monte Carlo. Las Vegas algorithms, they may not be right. I'm rolling the dice whether they're going to be right or not. Excuse me. I'm rolling the dice with the running time. They will always be right. That's the difference. Okay? So the running time holds an expectation, but the algorithm could go on for who knows how long. For example, if I'm, oh, never mind.
So like, what are the examples? So like Monte Carlo was the one we saw was the contraction algorithm. So there you do this like thing where you just walk through and you randomly you pick an edge at random, contract the 2 vertices, and then repeat. And then you do that until you're left with 2 vertices, and then there's some number of parallel edges going between those, and then that's the cut that you output for that run. And we showed that outputs a specific min cut with at least probability 1 over n squared. So there you're correct with low probability. But then how you take something that like an algorithm that is correct with low probability and then try to turn it into something that outputs the correct answer with high probability is you just repeat. As you keep like in there you'll keep repeating the contraction process, and then you'll have a set of min cuts that you found if you repeat k times, and you just return the smallest min cut that you found out of those k runs. And so the idea is then is like, well, okay, how big does k need to be in order to make it so I'm outputting a min cut with 1 minus 1 over n or something like that. And I think it ended up being like n squared log n, so it's like a n cubed log n algorithm or something like that.
So a simpler example, say I'm rolling a dice and I want to get a 1. So I can design 2 algorithms for this, right? I can roll a dice like roll a die a bunch of different times, hundreds of times, and then with high probability on one of those times I'm going to get a 1, right? I don't know what the number is, but we can figure out the number that if I roll it this many times with high probability I'll get a 1, right? Or I can roll it, 6 times, or I can roll it just until I get a 1, but in expectation it'll just be 6 times, right? Because I expect to get a 1 in the first 6 rolls.
So I would know that distinction to start with. But then were you asking like specific? Do you need to know like specifically like the proof for Karger's algorithm or the contraction algorithm? Yeah.
Don't worry about it.
Don't memorize. don't memorize proof for the sake of like, well, we have to be able to reproduce this. Like knowing proofs at a high level is like, I know that's vague because it's like, well, if it's too high of a level, then you don't like extract like the concept we might test you on or something like that, and then we're lying to you right now. But like,
You should know concepts instead, like this die thing.
yeah,
You don't need the specifics of the contraction proof aren't too important.
like I think it's good to know, like on the homework we expect, like you needed to use the facts that that proof ended up showing that if you fix some min cut, that min cut gets outputted with omega of 1 over n squared probability, right? So like knowing like maybe that nugget of information is good, but knowing that proof, that's probably too specific of a thing to try to do. So I think there's like a balance to kind of knowing things that like proofs that like kind of extracting nuggets information from the proofs, and then that's how like in terms of like conceptual understanding how far you should go, and then the rest of your time to spend practicing problems. I know it's 24 hours till the exam, so it's practicing at this point might be a little bit. If you haven't been practicing throughout the semester, then it might not go so well. But
What are some of the big things we need to know about hashing? Just like the two goals of the hashing function?
I mean, you can review I think all the hashing stuff is reasonably important. You don't need to know any of the field theory things that people were asking about on Piazza, so don't worry about that. But yeah, the goals and why the like naive hashing schemes that we came up with at first were no good. Yeah.
Can we go over this?
Yeah. So the first one, I have a universe U that has n things in it, and I have m slots to hash into. And this was deterministic hashing. So for each thing here, I assigned it some arbitrary slot, right? And then we counted the total number of collisions. The only things that collide are pairs of elements in the same slot. And so there were like the probability, how many collisions are there?
You can't reduce the number, it's always 1 over n, right?
1 over n squared. 1 over m, maybe. Yeah. 1 over m.
I think you're flipping
m collisions. n squared collisions, something like that.
No, I think expectation is going to be 1 over.
Okay, but that's deterministic. So then the problem with this was that if I don't want to minimize the total number of collisions, I want to minimize the probability that two items collide. And in any deterministic hashing scheme, I have to pick which spots the items get hashed to. So two items hashed to the same spot will always collide with 100% probability. And that's no good. So instead, we came up with this random hash scheme where each item in here just gets randomly assigned to a slot. It's not the same slot each time. I get an item, I randomly assign it to a slot. And now the probability of collision is as low as it can be, right? The probability that a pair of items collide is just the probability that they both get mapped to the same slot, which is 1 over m squared, right? But now the problem is I have to remember where I hash each item, and that's just as hard as the problem we were trying to solve, right? We end up having to store as much information to remember that as we are trying to store to start with. So that's no good also. So instead we came up with this a little more sophisticated thing where we chose, instead of randomly mapping each one, we chose at random some numbers that we're going to choose at random each time, and then we use those to sort of randomly map things, and then we show that the probability of collision is low. Those are the three that we went over. Yeah.
Well, you did know how to write like the dual of a linear program that's formatted as a summation. So if we have like the linear program called max flow, for example, we know how to take the dual of that. Or is it something?
Yeah, you should know how to take duals.
Okay.
you want to go over something like that,
Can you
or?
go over like the dual for like max flow, for example?
Oh, you mean like the typical? I mean, we did the dual for. So if you formulate the max flow as like summation, like paths.
Yeah, summation like
Yeah.
flow, whatever flow summation.
I mean, that gives back min cut, right? So if you're trying to max, so FP. So this is like, so F of P is the amount of flow we're sending along some ST or ST path, right? And then we're going to have a variable for each, and this is just the, we'll say this is the set of all ST paths. And so what's the constraint if we formulate it this way? Constraint. Right, so how do we write the capacity constraint?
So the sum over.
So for us, how many capacity constraints do we have?
It's like for all edges in P, right?
It's for all. What has to be true?
Flow on the edge, or flow on the path, I guess, is less than.
Flow on which paths?
The flow on all the paths.
Such that.
flow on the edge is less than the maximum.
But first, what do I put here? In terms of what am I summing over?
So the flow on all the paths that contain E is what's the E?
Right. So you're saying is that we sum over all P such that all such that this edge exists on that path. That whatever flow values I allocate on the paths that go through that edge, those have to sum to be less than the capacity on that edge. And so we're kind of, because we're formulating, we have a variable for paths themselves. The conservation constraints are sort of implicit, is that we're just automatically assuming that the flow is maintained throughout the entire path. So like, there's multiple ways to formulate problems as LP. So they get like the typical, like when we first introduced max flow, min cut, like the max flow formulation we had, like you can formulate, like we just say like you can, your variables are flows on edges instead, or you're allocating a flow on each edge. And then you can still, that's still a linear program, which is another way of formulating it, right? Yeah.
What is CE again?
Sorry?
What is CE? The one like FP?
What are you pointing at this?
Capacity.
Oh, C is the capacity on that edge.
Oh,
So
okay.
we usually, okay, what do we not C? What do we usually call this?
U.
UE, okay. We'll do UE to stay consistent. Okay, so like this is it's like, we wanted to take the dual of this.
Do we need the flow balance constraint too, or is that just?
So that's what I was saying with like, because your
Oh.
variables per path. If you were to do it, so like that's why for if you just allocate on an edge, like just allocating flows on edges, there's no relationship between the variables on their own. Then you have to directly encode flow conservation as an explicit constraint. But here it's because like the variables themselves are maintaining like its entire path. I'm just saying allocate the constant flow along that entire path that automatically ensures conservation. So all we have to do is ensure capacity.
So you need like a dual variable for each edge, right?
Great. So I don't know, we'll just call these XE for each primal constraint gives us this dual variable. So it's going to be in the dual, it's going to be a minimization problem. And what's our objective going to be?
Minimize XED.
Minimize XE. Yeah. Right. Because Because for the remember where you get your multipliers for the dual, right? This comes from the right hand side of the constraints. Everyone good on that? Where that's coming from? Okay, so how many constraints am I gonna have? Or what? There's gonna be a constraint for each path, right? What's going to be so what you want to do is you want to say, like, it's a little bit easier when you have like a table to actually, it's like a transpose thing. So here you just want to think, well, if I have the dual variables that I sum over here are is once I fix a constraint, I want to see, sorry. So once I fix a path, I want to see which xe, or which constraints over here did that path appear in. That path variable, this f of p, appear in. So I look over all these constraints, which f of p will appear, will have, will edge e appear. What's that? The ones that contain the edge. No, so okay, I'm fixing a path, right?
Edges contained in the
Right. It's just all the edges that were contained in it. And then where do I get so it's going to be a greater than, because it's a min problem. But then where do I get the multiplier on the right hand side?
The coefficients are not true.
It's the coefficients from here, which is in this case this one. So that's an example where it's like summation. So you just want to, and then this ends up being like if you restrict xe, so if xe, if we instead make it an integer program, that we argue that this is actually a min-cut formulation instead. So that's what we saw. So if you formulate the LPs themselves, we proved independently of doing anything with linear programs that max flow equals min-cut. But then, at least here, by strong duality, you have that the fractional min-cut is equal to max flow is a linear program itself, so it's equal to the max flow. And then we had this other argument that says, well, there's always some integral solution that is optimal for the fractional LP as well. But don't worry too much about that. I mean, this is in terms of being able to take a dual with like not something that's explicitly defined. Sorry, you
have xe again.
What's that? UE times xe. UE's this is the capacity. Again, variable. This times xe.
Right, but like, what does it mean conceptually when you're minimizing that sum?
Yeah.
You're minimizing.
Like,
Okay, so like, why is it min-cut? Is you're saying?
Yeah.
So you're assigning. So if this is restricted to 0, 1, I'm picking some subset of the edges, right?
Okay. Yeah.
Such that if I multiply the capacities on those edges that I pick, I want to minimize that. So without the constraints, you're just picking like some set of edges in the graph. But this ensures that whatever subset you pick, if I look at any path along from S to T, there has to be at least one edge from that subset I picked in that path. And then that ensures that it's a cut, right?
Also, it's me.
So if these are the set of edges that I set x equal to 1, it wasn't the case that it formed a cut, that there existed some path that implies that there exists some path from S to T such that So let's just if the set of edges that I picked didn't form a cut, then there exists some path from S to T such that none of those edges belong in this subset that I picked. So these are like the XE that I set to 1. But then this would violate, this is some particular path, and this would violate this constraint. That this is some path where some of the XEs that I picked, it's not greater than 1. So I know that that forms the cut. So then at that point, the possible solutions I can pick here are just the set of ST cuts. And then since I'm just multiplying the value of the cuts that, once I set the XE, this is going to be the value of the cut I picked. Is that good? Or, yeah.
So like, would we have to explain what XE is conceptually, or could we just say it's
No. So we asked you to take, well, I mean, that is something that if you take a dual and it's like, what problem have you formulated in the dual? That might be something that we ask you, and that you just kind of being able to interpret an LP and say, is it this some problem we've seen before? Is probably something you want to be able to do. It's not always the case that you take the dual and it has some natural interpretation of some other problem, but in some cases it is, and you try. And at that point, it's just a matter of it doesn't. If we just gave you this LP, could you be able to say this has been cut? That's something. That's probably a good idea.
But on that last test where we did the knapsack thing, the dual, that doesn't really have any meaning. It's just a thing.
Yeah, right. So that's the case where we didn't. And I wouldn't say it doesn't have.
Well, it has some meaning that we haven't talked about.
Yeah, right. So it's not necessarily it's some problem that we've seen before. Yeah, that's right. It's not always the case that you take the dual and it's some problem that you've worked with previously in the semester.
Even these XEs don't automatically mean this, right? The XEs are just variables that we get from taking the dual. Like Damali keeps saying, it's like a mechanical process, and these are just variables that we get. But this is just one way to interpret these variables, right?
Yeah, you want to. There is a distinction between LPs and problems, right? Is you want to be able to form the LP in itself is just optimizing some. I mean, your just linear program. And so you would need to once you have LPs, you should be able to interpret it as make the connection between an optimal solution to the LP gives me the optimal solution to some problem. So you don't want to. It's not like the problem is necessarily encoded within a specific LP. It's it's arguing that this LP captures the problem that I'm trying to solve is a better way to think about it. Okay, so that's some linear programming.
So if we formulated it the other way, right, where we had edges and then also vertices for the floating on stuff, could you still take the dual in the same way then?
We had.
It wouldn't be the same dual, but
Yeah.
And like an XD or something like that, right?
Yeah. So it would be. That's a trickier dual to take.
Okay.
But yeah, it would be different. But then you end up with an LP that looks totally different than this. But it ends up you can argue that it captures min cut, but it's harder to see that. It's this is much clearer that this, in terms of you can just make this nice little path argument out of the edges I didn't pick. If it isn't a cut, you get a contradiction. But sometimes it's the harder argument to you have some LP and then you have to take several steps to argue that this does in fact encode some problem. But I mean, I think it'd be a good exercise to go through and try to take it's a bit trickier because it's kind of weird to. That one's not as straightforward in terms of where, when I'm translating, which dual variables appear and which constraints over here. But, yeah.
So on the one homework that we had, that had a question that could have been answered with computational geometry stuff, there were also answers that didn't use it at all. So on the final
which question was that?
homework for problem 1, I believe.
Was it just the one computational geometry question you've had?
Right. So on the final if
was there an answer that didn't use computational geometry stuff?
We solved the problem without.
So we didn't grade anything.
What do you mean without using?
What was the?
So what's a non-computational geometry solution?
Yeah.
What?
You want me to pull it out?
Yeah.
No, just summarize the solution.
I think so. For the first one, you wanted to find all of the whatever optimal points.
Yeah.
Yeah.
So if you just pick a point in the set and then go through all the other points in the set, and if they are invalidated by the other point being optimal, you remove it.
What was the running time that's needed?
This is n time h, so yeah, something like that. I mean, like most
N times
h is the number of things in the solution itself.
Do you ever see the problem?
I think we remember the
But
problem.
anyway, the question
Yeah,
that I was gonna
that's
ask,
fine. I mean, that's still the question, like,
if you're like strongly hinting at this concept, but we solve it a different way, that's.
oh no, that's fine. Computational geometry isn't a set of concepts. It's a computational geometry question, right? Even if you didn't use like hulls or anything to solve it, doesn't matter. Yeah, don't worry about that.
I think we should pay
Yeah,
attention
yeah,
to within computational geometry.
Just the little bit we talked about. It's
I would know like why they have those, know what those like algorithms do. The idea of an output sensitive algorithm is probably a good thing to know. Like why it's the difference between something that.
if you're having trouble figuring out what the algorithms are from the notes, there are a lot of like simulations online that like graphically show you what the algorithm does.
That's the nice thing about geometry. Yeah.
Yeah, because these like two algorithms are the most popular in computational geometry. I'm sure you can find a nice simulation. And it's I find that much easier to remember what the algorithm does by watching like a 5-minute simulation than trying to read the algorithm.
Is there any other important topic we should cover?
That we didn't. I mean, MP completeness is still on the table.
Yeah.
So it's
Hopefully.
like something similar to second midterm.
Yeah.
Yes, yeah. Like a reduction like that.
So okay, maybe something I'll point out for. So just remember, I don't know if we went out over explicit example in class. So a lot of the reductions that we've done, is that you transform the instance, and then that algo 2 just like runs the oracle and then outputs the answer, right? That's like what your homework had. That's what like the one on the exam was, right? Is that once you have the transformation, then you can just take that oracle or whatever, that polynomial time solver for the transform instance and go. But just keep in mind that you're able to. It's valid or kosher to call the oracle multiple times. If that makes sense. Yeah. As long as you call it a polynomial number of times.
Is it still the case that we'll be given like a problem to reduce from?
Yeah, we're gonna like make you know a subset of like problems and like pick the right one to reduce from or whatever. I think we haven't like practiced it.
And please do the reduction in the right
Yeah,
direction.
do in the right direction. So a lot of people.
Or we'll just give you no credit.
Yeah, so just make sure like before you even start writing, thinking of like it's kind of like maybe tempting to say like, oh, there's like if there's a graph problem, it's like I'll start drawing graphs that relate to monitor like a stat formula or whatever. But then you're not doing the right direction at that point. That's like on the exam. I think that's what some people did. It's like, well, if I draw, they start drawing graphs on like the first page, and just make sure like sit down and figure out the direction first, and just make sure you're trying to show you have some problem. You're trying to show it's harder than an already known to be hard problem. So you're going to take the already known hard to be hard problem and reduce it to this new one you're trying to show to be hard. So just like run through, make sure that's the direction you're going in before you gung-ho start to do the reductions. So. Yeah.
Two things that just to show up reducing A to B shows that B is at least a part of that.
Right.
Yeah.
And then second, if you call the oracle like a polynomial number of times.
Yeah.
You do it like a log number of times, like it's n log n considered a polynomial.
Yeah, no, yeah, anything. Like anything, right.
It's not like into whatever. Or into the n.
Or n2 to the n or constant raised to the n. I mean, just at
Anything,
that point.
anything that's at most n to some constant is polynomial, and n squared is bigger than n log n, so you're fine.
Like you can replace any logarithmic term by just, if it's like log n, it's n is higher, so that's bounded by if you're multiplying.
Yeah.
It seems like it's been kind of assumed previously that like if we like can find the reduction that you would just run the same oracle once. So you're saying that we would need to explicitly.
So it doesn't you have to, you're going to have to do this, but keep in mind that's something you can do.
Okay.
Is that you can, like, I don't know if I want to go through a specific example. So you can like transform the instance, run the oracle, see the answer. If it's yes, maybe stop. If it's no, modify your what you're working with in some way. Call it again on that whatever you modify. And you can keep making calls of the polynomial time solver. And then the reason, as long as it's a polynomial number of times, if you take some polynomial times a polynomial, it's still a polynomial. So it still implies that the idea is that you're still implying a polynomial time algorithm to the already known to be hard problem. So.
Is that true?
Yeah.
Really?
You don't believe me? Why not? Isn't it how you just said it? That's valid.
Like I thought if the output of the like if you wanted to switch the yeses and nos in the output of the reduction, then that takes it out of being NP, like or something.
We're showing NP hardness to start with, so it doesn't have to.
Okay, maybe for NP.
As long as you can show NP hardness any way you want. You said
Yeah, that's for being in NP.
But it's a way of, even if you're working with. All right, thanks. So what time is the exam tomorrow at 7? So show up on time. What's that?
Yeah, it's in the same classroom.
Yeah, it's in the same classroom.
I think.
So
Yeah, 7.
for my homework 4, I said that I had no submission for homework 3, but I like brought up the PDF on COMPSCI. I'm like, so I'm not.
Wait, so for homework 4, you did said there's
for homework 4, problem 3, I got no credit because it said no submission. But on COMPSCI, when I brought it up, it was there.
Alright, I have no idea. I didn't take a look.
So it said no submission for what? Okay, what?
Like on the grade book, it said no submission for part problem 3 of homework 4. But then I went to my Sakai submission, like opened up the PDF and it was there.
So which part of which homework? I keep missing it.
Problem 3.
Problem 3 of homework 4.
Okay, so it could be like whoever graded it, like graded it after it. So just email us and we'll go through it.
Yeah.
Okay.
Just email us.
Are you posting on Piazza? It says on Sakai, didn't turn into sign it form.
Didn't turn it inside.
Yeah.
Can you rate you did or?
I did, like I have it,
Yeah,
Was it on Sakai?
there was some technical error in your
submit. Was it on Sakai when you checked?
Yeah, you got full credit.
No, it wasn't, like it said I had submitted.
Okay. Yeah, okay. So email us the homework. You might get penalized because you didn't actually submit.
I didn't see this, like, I think it's gonna be pretty clear that I did
Because he said
not.
that, yeah, he just said
Yeah, no, we'll talk to,
this.
it's up to the Moya ultimately, but we'll go ahead and grade it. Just like, in terms of what we'll do, we will.
How long is
I like posted my PDF.
Yeah, oh, you already posted it? Yeah. No, we'll
Yeah, so he made it about, we tried to make it twice the
How
length.
important do you think it is to like review
So 2.5 hours.
assignments like in depth and like look at the solutions? Like,
Yeah, I mean, the
I
thing
mean, they
about.
build on all the shit in the class, so like.
Yeah, so, yeah, I mean, none of the problems on the exam are going to be hard as the problems on the homework.
Yeah.
But, like, I
But
think
would- like, are they,
reviewing
like-
problems, just if you know, you can recite, like, the problems from the top of the head. I think that gives you, that implies that you know the
You know
concepts.
the more basic stuff that would be on the test.
Alright,
Cool, thanks.
Yeah. I mean, I studied them some. So.
The question here are just like random selective knowledge, like you do it, then you do it.
Yeah.
I literally had every like question on there except for